substantially easier than factoring. So it's much easier than our last unit. That's not saying that it's like a joke in this unit that's super incredibly easy. It's just easier, right? There's different difficulties. Trigonometry is a unit that's very like applicable. Like we're finding like the lengths and angles of triangles. So you actually like it's more tangible, and you can see why we're doing it. Page 199. You can see why we're doing it a lot more than in our previous units, which is really nice. We're going to do, I think, 3 classes is my goal, and then we're actually going to start a project. So criteria C and D project. So we're going to get through this unit. We're going to do a CD project and have a unit test before Christmas break. Yes, that's all. So today with trig, we're going to kind of go back to like where trig came from back in like Pythagorean's day, when he was like playing with triangles in his spare time and thought triangles were super cool. And like mathematicians back in the day had a lot of time on their hands, and they were just looking at comparative pieces. The stuff we're doing today, that being said, is just, you're going to kind of be like, why am I learning this? Why does this matter? Totally get that. Tomorrow's class, you're going to see the why behind it and why it's a little bit more relevant. In my perfect world, I would have done this as like a double block. It's like 2 math classes, so we could do the 2 side by side, but that's not going to happen. So this first page, so page 199, are we all here? We used to do this, and by used to, I mean like last year as an actual investigation. So summative investigation, we used to give it to you, but we don't have time for that. So you guys save out on an investigation this year. What you would have done is you would have taken a ruler and actually done some measurements. I'm going to tell you those measurements because I doubt anyone in here has rulers. But these diagrams on this page are actually 2 scales. So you could take some measurements. So this is what ancient Greek mathematicians did. They were like, let's measure some triangles. So they drew a triangle that has an angle right here of 35 degrees. We know it's a 90-degree angle. Could we determine what this angle up here is? How? Go ahead, Drew. Good. All triangles add up to 180. Do you guys agree that this angle there would be the same as this angle? Do you guys remember that? Would be the same as this angle, which is the same as this angle, since all of these would be 90 degrees throughout there. So really, it's like the same triangle, just getting a little bit bigger each time. It's a proportional triangle. So if you went through and you took all of these measurements, these are what those measurements would be. So this is 1.4 centimeters, 2.8 centimeters, 4.2 centimeters, and 5.6 centimeters. So like that's our vertical piece going all the way up. Our horizontal, the distance between each like increase is 2 centimeters. So this is 2, this distance is 2, 2, and 2. So some guy back in the day was like, look at this triangle. All of these triangles are similar. They all have the same angles, making them similar triangles. Then he's like, let's look at the sides and see if there's a relationship between the ratios. So remember, a ratio is simply a division statement. So he was going to divide the vertical side, so our like 1.4, by that horizontal side. So dividing the 2 legs of our triangle that aren't the hypotenuse. When he did it on his first triangle, he got 0.7. On the second triangle, so if this is 2.8, so looking at this triangle, so 2.8 divided by 4, he also got 0.7. And he was like, man, that's kind of cool. The third triangle was 4.2 over 6. He also got 0.7. His last triangle, 5.6 over 8, he also got 0.7. So then he was like, he did this thousands of times, making his triangle consistently larger or smaller, and came up with the statement that the ratio of 0.7 is related to triangles with 35 degrees. And he was like, I'm brilliant. Can you imagine doing that in your spare time? Kind of cool to come up with like that concrete of a pattern, but also super boring. So then they're like, hey, let's see if there's something similar with this triangle. So you went to this triangle and was like, hey, this is 58 degrees. Let's draw our triangles with 58 degrees, a 90-degree angle. Let's draw these triangles and see what we get. So on this one, our vertical height is 2.4, and then 4.8, 7.2, and 9.6. And now each time here increases by 1.5 horizontally. So when he was drawing the triangle, this is what kind of worked out to be his pattern. Then he did this division. So the first triangle gave him a ratio of 1.6. The second triangle also gave a ratio of 1.6. The third still gave 1.6. So he concluded that you're going to get a ratio of 1.6 connected to a triangle of 58 degrees. If you go back, so like the textbooks that like I had, and I swear I'm not that old, but the textbooks back in the day, they would have in the back pages, like in your index, all triangles with all your different angle degrees, and then these ratio results for you. And you could use this, like the data that they came up with, to use for trigonometry. Now your calculator, you know the buttons on your calculator that say sine, cosine, tan? Those buttons do these ratios for you. But back in the day, they would look them up. I always had the buttons. I'm not that old, but they gave, in my textbooks, they would give me like the pages as well as the buttons. Did they ever use those pages? No, I thought they were dumb. My teachers also did. Why not use technology when you have it? But that's where it like came from. And so they were noticing, look at this, all these triangles have this pattern. That's what our trig ratios, which we're going to get into, where they're coming from. Okay, turn the page. So as they're back in the day, so as our ancient Greeks are looking at this, like, hey, we need to make our terminology here a little bit more clear. So let's label our sides of our triangle. Oh, sorry, Khalil?
So just to make it clear, so the side divided by 1 is always the same when you increase the size portion.
For each type of triangle. So like for a triangle that has angles of 30 degrees, this side divided by this side is always going to give you the same answer. For 31 degrees, the two sides will always give the same answer. It's going to be really close, but it'll be a slightly different ratio. But always going to be the same. Really good question. Okay, so they're like, okay, let's make this a little bit easier to describe. So let's start a practice for labeling a triangle. So back when you first learned Pythagorean's theorem in grade 8, we said we have a hypotenuse and two legs of a triangle. Those legs were always side A or side B, correct? A and B, you could always flip-flop to your heart's desire. Now they're like, this has to be a little bit more specific. So they came up with using our hypotenuse, opposite, and adjacent. So when you label your triangle, your hypotenuse, spell it correctly, is always the side opposite your 90-degree angle. Your hypotenuse is also always your longest side. This is specific to right triangles. We only care about right triangles in grade 10. I'll word it like that. So then it says the opposite of angle X, this is always talking about a specific angle, is called your opposite side. So what that means, if this is my angle X, the angle they told us we're caring about here, the side that's farthest away from it, we're going to call our opposite side. Or you might say OPP for shortened. The side that's attached to that specific angle, that's not your hypotenuse, is called your adjacent side, or ADJ. So like, okay, so now we can talk about this a little bit better. So on the previous examples, we were always doing our opposite divided by our adjacent side. So they found a pattern when they did that division before. Let's go through a couple examples of this labeling. So it really matters what angle you're talking about, right? Because that opposite adjacent will change depending on the angle. So the angle will always be given. So in this first example, our angle is down here. So first off, always start, I think it's easiest with labeling your hypotenuse initially. Opposite that 90 degrees is our hypotenuse. The side that's farthest away from your angle or not attached to it is our opposite side. And the side that's connected is your adjacent side. Okay, on the second one, they like turned my triangle a little bit. So our hypotenuse, still opposite that 90-degree angle. My angle we care about is up here. So way over here is opposite. Attached to it is our adjacent. So like, okay, now we have a way to like talk about our sides of our triangles a little bit more clearly, as well as that will apply to all of our cases, right? Like just kind of gives us more general terms. So then they're like, okay, let's give some names. Why they came up with these names, I don't know. But they decided when I'm talking about the opposite side divided by my hypotenuse, we're going to call that the sine ratio. When we do our adjacent side divided by our hypotenuse, we call that the cosine ratio. When we do our opposite over our adjacent, we're going to call that the tangent ratio. So on your calculators, it's sine, cos, and tan. The examples over here, these are the inverse ratios. So you'll notice like it's cosecant, it's opposite and hypotenuse are flip-flopped. These are not grade 10, so we're not going to do these. These are not in our curriculum. Not level 7, 8. It's just like the flip-flops of them. You'll cover that more in grade 11. Why we don't do it in grade 10, I don't know. It's not that it's that much more difficult. We just don't, so you don't even have to worry about them. Turn the page. So to remember those ratios, we came up with the, I don't know, mnemonic of SOHCAHTOA. So where does that come from? And I like writing it this way. So sine is for opposite over hypotenuse, or so. I would write it down like this. Cosine is for our adjacent over hypotenuse, and then tan is for opposite over adjacent. So it's just a way to remember what each ratio is. I find writing it out like this is just also the visual prompt for which one's your numerator and which one's your denominator. You are going to say SOHCAHTOA so many times in the next 4 weeks. Every grade 11 and 12 student knows what SOHCAHTOA is. Is that okay? Yeah? Okay, I'm going to skip class example 2 because I find it really confusing because there's not a diagram. So class example 3. So we're given this triangle and let's go through what our ratios would be. So all we're doing here is division at this point. First step, let's label this triangle with our sides. So which number, 21, 20, or 29, is my hypotenuse? Just shout it out. Good. So this is our hypotenuse. Which side is my adjacent side to angle A? Good. Making 20 my opposite side. So if we go back, so our sine ratios are opposite side over hypotenuse. They give us that. So that's going to be 20 over 29. Gives us a ratio of 0.690. We don't know what angle A is here. You could go back, like I was telling you in your textbook in those pages, and then look it up, find which ratio gives you, 0.690, and be able to find and identify which angle matches that. That said, in 3 classes, I'm going to tell you how we can use our calculators to figure it out. Our cosine ratio is our adjacent side over our hypotenuse, which is 21 over 29, which gives us a ratio, like when you do that division, of 0.724. This question specified to the nearest thousand. That will vary. Make sure you're reading correctly. Our tangent ratio is opposite over adjacent. So I'm going to get 20 over 21, which gives me a ratio of 0.952. realistically, like practically speaking, these ratios not super helpful. But in our subsequent classes, I'm going to teach you then how to use those ratios to find lengths or angles. So they become more helpful from here. This is like step 1. Does that make sense so far? Cool. Turn the page. So on this triangle, 3, 4, 5, do you guys recognize that that's like one of the Pythagorean triplets? Yeah? Good. 5 is our hypotenuse. 3 is our opposite. And 4 is our adjacent. Let's go through and see what these are. So they tell us our sine ratio is going to be 3/5. So our opposite over hypotenuse gives us that 3/5. Our cosine ratio is our adjacent over hypotenuse, which is going to be 4/5. Our tan ratio or our tangent ratio is opposite over adjacent, or 3/4. Go ahead, Khalil. It's just like triangles for you to start recognizing they're always 90 degrees. So 3, 4, and 5 is always going to be a 90-degree triangle. It's not something we expect you to memorize. It's just something you might have recognized because the number of times you probably did Pythagorean's theorem on a 3, 4, 5 triangle is kind of comical. Okay, I want you to try and do 5 on your own. So they tell you as well in rational form. Do you guys remember from grade 9 doing like whole numbers, integers, natural numbers, all of those things? The different terms for numbers. A rational form is saying you should be writing it as a fraction because all rational numbers you can write as fractions. So by saying rational form, it's saying leave your answer as a fraction. So try this one on your own. First step is to label your triangle with the appropriate sides. When we're talking about fractions as well, remember we always leave in lowest form. So for sine, it's our opposite over hypotenuse, which is 30 over 34. Both of those are divisible by 2. So I get 15 over 17. You have to leave it in lowest form. Our tan ratio or tangent ratio is opposite over adjacent, so that's 30 over 16. Also divisible by 2, so I get 15 over 8. Cosine ratio, adjacent over hypotenuse, so 16 over 34, which gives us 8/17. Have to leave it in lowest form. Okay. Your workbook does a really good job of incorporating other units. That being said, we don't follow the order of your workbook. So this next question has a square root symbol in it, root 2 here. That's because later on in the spring, we're going to do a unit that has to do all with radicals or square roots, cube roots, that sort of thing. So they're like trying to incorporate other units here. I'm not going to give you a question like this on your test because there's a lot more pieces to it. We're going to do it in kind of a simplest form. So in this question here, root 2 is my hypotenuse. Both other sides are 1. So does it really matter which is my adjacent and my opposite? No. But let's pretend like they weren't the same. Notice here it says sine A. So what that means, it's sine of this angle A over here, which forces this side then to be our opposite and this side to be our adjacent. So we're going to get 1 over root 2, or opposite over that hypotenuse. Cosine would be 1 over root 2 as well, but it's our adjacent one. And then tan is 1 over 1, which is just a whole. So this next example is really trying to emphasize looking at that specific angle that is in question. So in this first example, we have two angles, x and angle y. So that's going to change our adjacent and opposite sides. So regardless which angle we're talking about, 10 is always going to be my hypotenuse. So I'm going to label angle x in blue. So that makes 6 our opposite and 8 our adjacent side. So when I do sine of x is our opposite over our hypotenuse, I get 6 over 10. What does that reduce to? Shout it out. 3 over 5. Okay, and then I'm going to go down and do the cosine of x, just so we're doing all of x. So that's our adjacent 8 over our hypotenuse, which both those are divisible by 2 again, so I get 4/5. When we go to look at y, my sides change because now this side here is my adjacent side. And this side over here becomes my opposite side. So our sine of y still are opposite of our hypotenuse, but our sine of y is now 8 over 10, which gives us 4/5. Our tan is our opposite over our adjacent, so 8 over 6, which gives us 4/3. Does not look like a 6. Okay, I want you to try and do the next one on your own. So label your triangle very carefully. Make sure you're looking at which angle is at question. So for the cosine of A, our adjacent side is 5, hypotenuse 13. For the sine of A, our opposite is 12, hypotenuse is 13. For B, those two are going to flip-flop. So now 12 is going to be our adjacent side. 5 is our opposite. So our cosine for B is going to be 12 over 13. Our tan for B is our opposite, 5 over our adjacent, 12. Is that okay? Good. So let's talk calculators for a moment. For this entire unit, you're fine with the calculator used in grade 9. That will be more than sufficient, works just fine. That being said, for most of the rest of the year, we require calculators. The first unit we are going to do when we come back after Christmas break, you require a graphing calculator. I strongly encourage, if you already have a graphing calculator, to use it this unit. It's just going to get you more comfortable with it. The graphing calculators I prefer are the Texas Instrument ones, or the TI versions. Does anyone in this room have the Casio? Cool. There's another like brand, Casio. It's actually probably a better calculator. It does more, like it's a better computer, you would argue, to the point where on your diploma, certain versions of it, the government of Alberta won't let you use it. Your workbook uses examples using your TI calculators though, so that's why I prefer that one as well. So all the examples and stuff, you'll like the buttons that it tells you to press are already here for you in this workbook. So that's what you'll need starting in January. Does everyone have a graphing calculator already? Maybe not with you today, but you have one like in your possession. Cool. So that's what you need. You need a calculator for today, but you definitely need one for our next class as well. These are the practice questions. The last one's number 11. Nice spacing. You should easily get through these today. Take your time on them. Make sure you really understand this. This is like our building blocks.